Welcome back to Earth Science from Chapter 3 of your textbook, The Good Earth. We're now talking about near-Earth objects. And on your screen, you see a picture of an old video game from the late 70s and early 80s called Asteroids, in which a rocket ship had to shoot lasers to break up these larger asteroids to protect the Earth. Now, is that a means by which we might be able to protect the Earth from near-Earth objects, send out a spaceship to blow up the asteroids before they hit us? Well, it certainly is a possibility. In Chapter 3 from The Good Earth, we're going to talk about the characteristics of near-Earth objects, and that does include asteroids and meteorites and meteors. We're also going to talk about the different types of impact features that you can find, the impact hazards that exist, and of course the end of the book is basically the end of the chapter, is essentially going to give us the warning to beware of flying rocks.
Back in 1992, a football-sized meteorite crashed through the trunk of Michelle Knapp's Chevrolet Malibu Classic in Peekskill, New York. That meteorite was at one time a meteor when it was moving through our atmosphere and glowing brightly. And before that, it was an asteroid moving through space, an asteroid probably knocked out of its orbit from the asteroid belt. Asteroids, meteors that become meteorites, and comets as well are all known as near-Earth objects, or NEOs, and they are all those asteroids or comets that approach Earth. So what are the chances that a large space object will crash into Earth in the near future? Well, of course, that is the question. So the Earth and the Moon and other terrestrial planets all carry the scars of past impacts with asteroids and comets. As a matter of fact, this photo from Barringer Meteor Crater in Arizona, it's from about 50,000 years ago when a 50 meteor in diameter meteorite crashed into Earth. So an asteroid that passes into Earth's atmosphere is then considered a meteor as it's burning up in Earth's atmosphere. If it actually makes it to the ground and strikes the ground, then it's considered a meteorite. Now, 65 million years ago, it is hypothesized that a 10-kilometer wide asteroid struck the Earth and caused the global extinction event that took out the dinosaurs. So it's a pretty darn big crater here in Arizona from a 50 meteor in diameter meteorite. Imagine a 10-kilometer in diameter meteorite. That's what is hypothesized to have hit the Earth about 65.5 million years ago. Have we had any near misses from NEOs? Well, most near-Earth objects, NEOs, do not come close enough to Earth to be a real concern, but occasionally one may approach within the Moon's orbit, and that's a pretty darn big deal. So there's a lot of information on this slide. This first illustration that we see shows the Earth and the Moon. It gives us a scale of about 50,000 kilometers and shows us the number of NEOs that have come quite close to Earth's orbit. And then we can see kind of in that red print just below that illustration, the green arrow points to where an asteroid in 2029 is expected to fly by within 36,000 kilometers of Earth. And that's pretty darn close, and there's been other famous flybys of NEOs, and you can see those again. We can see the one that's expected to come through in April of 2029, one that came through in 2013. It's quite small, but it was really darn close. Much bigger ones expected to come through in 2028. That's something that we'll also be able to see quite clearly in the sky. So yeah, there's been plenty of near misses from near-Earth objects. So maybe this is something you've not really heard anybody talking about before, and that's because our understanding of near-Earth objects really dramatically increased in the 90s. So this picture on the left is the inner solar system, a chart made back in 1900 in which very few asteroids were recognized in the inner solar system. So that was about 100 years ago. Then in the 80s and 90s, we began to look at near-Earth objects with a little bit more vigor, and then in 1999 this new chart was drawn with more than 90,000 asteroids that have been identified, and all those little red ones are ones that we consider to be near-Earth objects. So yeah, they've always been out there, but we really know much more about them now than we did 20, 50, certainly 100 years ago. So asteroids and comets. Well, asteroids originate in the asteroid belt. Where else would they come from, right? The asteroid belt is a collection, a dense collection, there's a lot of them out there, of cosmic debris that's orbiting between Mars and Jupiter. And this cosmic debris is essentially debris that was thought to have been left over after the formation of the solar system. Remember, the planets become planets because they sweep out their neighborhoods of cosmic debris. They're big enough to have their gravitational pull create round objects. But in the asteroid belt between Mars and between Jupiter, there just wasn't a planet circling that could sweep out that particular section. So we got the asteroid belt. Now, gravitational attraction of Jupiter pulls asteroids out of orbit, causing collisions with other asteroids, sending those or other debris toward the inner planets. So essentially, everything is in balance until Jupiter decides to grab one of these asteroids. You can see Ceres, which is the big one that we've looked at very closely. And they pull one asteroid out of orbit, it smacks into some others, some debris flies out or other asteroids fly out, and those are the asteroids that move toward the inner planets. Let's talk about some of the characteristics of asteroids, their size, anywhere from a pebble to the size of Ceres, which is about 940 kilometers across. They travel at 16 kilometers per second or 36,000 miles per hour. And generally, asteroids are composed of rock and or metals. So you have some asteroids that are just all rock, and they're called stony meteorites when they come crashing down to Earth, and then other asteroids that have a combination of rock and metals, mostly iron and nickel. So let's go ahead and define again. An asteroid is flying through space. When an asteroid comes into contact with our atmosphere and enters our atmosphere, it's now a meteor. So a meteor is what you see zipping through space briefly, if you happen to catch one. A meteorite is when that asteroid burns through the atmosphere but strikes the Earth's surface. So about 90% of all meteorites that strike the Earth's surface are stony meteorites. And they are made up of rocks that are very similar to the Earth's crust. Now, some of those that strike the Earth have a combination of iron or a combination of iron and nickel. So some have stone and iron, some have stone, iron, and nickel, but all of these materials are the materials that make up the terrestrial planets. So scientists hypothesize that asteroids are the leftovers from planet formation more than 4 billion years ago, and that have essentially been marooned in the asteroid belt. Comets are different creatures altogether. Generally, comets are going to be larger than asteroids, oftentimes many hundreds of kilometers across. They travel faster than asteroids, 50 kilometers per second, or about 112,000 miles per hour. And they are left over from the cosmic debris that was part of the formation of the solar system. So mostly they are dust with ice and a rocky core. At one time, we considered comets to be these dirty ice balls. We thought they were just big, huge chunks of ice that had a lot of dirt and dust around them. But now we know that they're actually rocky core with some ice and then a whole lot of dust. So probably better to call them icy dirt balls. Some scientists, of course, hypothesized that during the heavy bombardment period within the first 2 billion years that the Earth existed, when there was still a lot of debris flying around the solar system before the planets had swept up all that debris, that comets very likely brought ice and other critical compounds to the early Earth. The common compounds that you can find in comets include cyanide and carbon dioxide and water. And again, we mentioned that scientists are investigating if comets could have supplied water in the early Earth's oceans. How do we know this about these compounds associated with comets? Well, back in July of 2005, the NASA launched a spacecraft called Deep Impact, and Deep Impact launched a smaller spacecraft called Impactor that actually struck Temple 1, which is a comet that circles the sun every 5 or 6 years. So it's pretty amazing they were able to do this, but the explosion from that impact allowed scientists to study the composition of comets. There are two types of comets. We have short period and long period comets, and pretty interesting. This illustration shows what's known as the Oort cloud, and so the Oort cloud is this cloud of cosmic debris that essentially surrounds our solar system. So when we talk about the heliosphere, the region of space that the sun is the biggest feature of, that would be this Oort cloud. Now within the Oort cloud is the Kuiper belt. That is the belt in which some of the comets come from. Other of the longer range comets come from this Oort cloud. So short period comets, they have time intervals of 200 years or less. So they can get around the sun and back to where they started in 200 years or less. And they originate in the Kuiper belt. And the Kuiper belt is beyond Neptune and well past Pluto. And that Kuiper belt is a belt of debris that circles the sun just outside of what we call our solar system. These types of comets are called trans-Neptunian objects, and they circle the sun in the same direction and at a similar trajectory as the outer planets, and they return to the inner solar system every few years. So our short period comets come from that Kuiper belt, and again, they're basically leftover cosmic debris from the beginning of the formation of the solar system. Long period comets, they originate from the outer limits of the heliosphere out in the Oort cloud, and they are disrupted from the Oort cloud by the gravitational pull of passing stars or nebula. So we're talking about just fantastic distances here. And they tend to return to the inner solar system over a period of decades to thousands of years in very irregular elliptical orbits. And those elliptical orbits cross the plane of the ecliptic at a fairly high angle, and much in the same way that Pluto crosses the plane of the ecliptic at a high angle. The plane of the ecliptic is that plane of the Earth's orbit, and really most of the other planets, the other planets, whether terrestrial or Jovian, are somewhere within a few degrees of the plane of the ecliptic, and Pluto is way out, way much higher angle on the plane of the ecliptic. So again, these longer period comets tend to come from the Oort cloud, or they do come from the Oort cloud, way out there at the outer limits of the heliosphere. And here's a nice, fairly simple illustration of the two types of comets, with the long period comets coming in from the Oort cloud. So that on the left, that little red line, that's just a partial path of that comet, because it's coming in from way, way, way out in deep space, whereas the short period comets, they're coming in from the Kuiper belt, which is just out beyond Neptune and Pluto. And the short period comets orbits the sun with similar paths to the outer planets, and then the long period comets have those wide, long elliptical type of orbits that cross the plane of the ecliptic. Not only asteroids strike the Earth, comets can as well. In 1908, an explosion of a comet in the atmosphere, so it didn't strike the Earth, it actually exploded above the Earth's surface out in Russia, destroyed a forest area the size of a major city, 2,100 square kilometers. It was massive, and we have pictures of the trees knocked down by that comet exploding in the atmosphere over Russia. Again, collisions with near-Earth objects can be catastrophic and can create global extinction events. So this was not really as bad as it could have been. Impact features that remain over geologic time from the collision of near-Earth objects with Earth are called impact craters. And there's essentially two types of impact crater. When an NEO collides with a rocky planet or their moons, they form one of either two types of impact craters, a simple crater or a complex crater. This crater on the left from Barringer crater in Arizona, which is from a meteor, is a simple crater formed about 50,000 years ago, and this was the first meteorite crater recognized on Earth, and that was about 1,200 meters across. So all impact craters have lots of broken rock around them. It's called breccia, broken up pieces of rock known as breccia. Fractures at the base of the crater. All impact craters have this ejecta, or pieces of rock and debris and dust that are thrown from the crater. All impact craters melt the rocks in direct contact with the actual crater, and because of a high heat and pressure, all impact craters alter minerals. Heat and pressure can alter the composition of minerals. Simple craters tend to simply be bowl-shaped, and they maybe are a few kilometers wide. Complex craters are typically more than 4 kilometers in diameter, and they have a central peak in the middle where the Earth is literally rebounded from the collision, where the actual asteroid or comet actually hit the Earth. There's a rebound that creates a central peak, and then they tend to have rim structures or ring structures around the rims of the crater from where the rim of the crater has collapsed. Here is a photograph of a simple crater from Mars. Bowl-shaped, pretty straightforward, 2,600 meters across, and the dotted line representing the ejecta blanket that is surrounding this crater. This is a photograph of a complex crater on the moon, 58 kilometers in diameter. This is a big one. You can see the central peak, the ejecta blanket surrounding the crater, ring structures around the edge of the crater. Again, that is where the rim of the crater has collapsed, and then also small, simple craters sort of surrounding it from other impacts, or perhaps even impacts that came along with this major impact. From studying craters, we've come up with a pretty good estimation on the crater versus the near-Earth object's size. So an impact crater tends to be 10 to 20 times larger than the colliding NEO. So if a 10-kilometer near-Earth object hits the Earth, then the crater might be 100 to 200 kilometers across. And an example, this crater in Canada, and really we only have the remains of the crater in the rock record, the estimated NEO was between 5 and 10 kilometers in diameter, and it created a 100 kilometer wide crater. More than 150 impact craters have been identified on Earth. A couple of them are identified in the oceans. Typically, ocean floors are less than 200 million years old, and those craters have been obscured by other geologic processes that are occurring on the ocean floor. But number 3 there, just off the Yucatan, also part of the Gulf of Mexico, that is the impact that was thought 65 million years ago to have caused the extinction of the dinosaurs. So the good news about these really big near-Earth objects is impacts, expected impacts, are really very infrequent. We go back 65 million years to the one in the Yucatan that killed the dinosaurs, about 1 million years to an impact crater from a large NEO in the Chesapeake Bay, and then about 100 years to the one that the meteor crater that we saw in Russia. So impacts of relatively small NEOs, 50 meters or less, occur at intervals of maybe hundreds to thousands of years, but those large NEOs, 10 kilometers or more, tend to be measured on timescales in the hundreds of millions of years. And here is the illustration of the potential catastrophic events that would occur if a 10-kilometer NEO collided with Earth. You know, we get the tsunamis, the wildfires, the air blast knocking trees down, hot fragments starting fires, and then the ejecta from the collision, creating a dust cloud and blocking out sunlight and cooling the Earth in the short period, maybe even years or tens or hundreds of years, but in the short term in terms of the geologic time scale. So what would happen if a 10-kilometer NEO collided with Earth? Well, it doesn't look like it'd be very good. And these are some of the expected events from a 10-kilometer NEO, this large fireball racing through the atmosphere, people at the impact site with just seconds to live. The air blast would flatten everything for hundreds of kilometers in every direction. A massive earthquake at the collision site. Ocean impact would produce giant tsunamis hundreds of meters high. Molten rock from the collision would rain down, starting massive wildfires. Huge clouds of dust. The ejecta from the impact would block out sunlight, cooling the planet for months, killing off most vegetation. And then lots of gas from the impact, sulfur dioxide and water vapor, will be added to the atmosphere. Some scientists hypothesize that NEO impacts are really the only major natural hazard that we have the potential to prevent. We can't stop volcanoes or earthquakes or massive hurricanes, but potentially we could develop the technology to prevent a major NEO impact. With forewarning, NEOs could potentially be deflected off course or destroyed. Scientists have already hit a comet with a spacecraft and landed a spacecraft on an asteroid. So it's not out of the realm of possibility that given enough time, we could do something to deflect or destroy an incoming NEO. So because we'd like to have that time, that forewarning, we have seen organizations created to detect NEOs. So current NEO search programs focus on the approximately 1,000 objects with a diameter of more than 1 kilometer in the heliosphere that we think are near-Earth objects. They're looking for fast-moving dark objects against the backdrop of space, so they're pretty tough to find. But these largest NEOs are the ones that pose the greatest risk, and because they are so much larger, they're easier to find than the small ones. And so it really doesn't make a lot of sense to look for the small ones. They're basically just looking for the big ones. And scientists map the position of those NEOs over time and chart their course relative to Earth, and definitely making that effort to protect humanity from this particular global catastrophe. As I will tell you many times in this course, scientists basically just classify things. If you were a shell scientist, you'd go to the beach, you'd come back with 1,000 shells, and you'd separate all those shells into different piles. You'd classify them. You'd have round shells, you'd have cone shells, you'd have red shells, you'd have white shells. And so when we talk about impacts of NEOs, scientists want to classify those impacts as well, and that scale is the Torino scale. That assesses asteroid/comet impact predictions. So the Torino scale, 0 is that an NEO in space will miss Earth or burn up in the atmosphere. 1, it will pass near Earth but extremely unlikely to impact. 2 to 4, minor chance of an impact. 5 to 7, a serious threat of impact. And 8 to 10, certain collision. And we don't have anything above, I think, a 1 at this time, but nonetheless, there are scientists out there looking for these NEOs. So this wraps up Chapter 3. The next chapter is Chapter 4. It's got significantly more content associated with it. It is the study of plate tectonics, and plate tectonics is considered to be the unifying theory of geology on Earth, pretty much explaining most geologic processes through plate tectonics. So it's a pretty important chapter. Make sure you have time to sit and watch that lecture. It's going to be a little bit longer than this one.